This lesson will cover sections 8.1 and 8.2, mainly dealing with confidence intervals. And the definition of confidence interval is kind of listed here. But basically, we want to take a sample mean and with a certain level of confidence, estimate what the value of the population mean might be. And keep in mind, x bar is the mean of the sample, which is also known as a statistic, and mu is the mean of the population, which is known as a parameter. A lot of times, parameters, the values of a parameter cannot be found, so we'll use a statistic and then estimate what the value of the parameter might be. So, a few assumptions. The distribution is normal and not skewed. So what that really means here is that we're dealing with a bell-shaped curve, or that Pearson's index is between -1 and +1. And the whole goal of this section is to construct this confidence interval from the given sample mean that will contain the population mean. Remember, that's with the variable mu, either 80, 90, 95, or 99% of the time. You can really construct any level of confidence, although these would be the four most major types of confidence levels. Next, how to construct a confidence interval. You would take your sample mean, then add and subtract a certain number, and that number is known as the margin of error. The way you find the margin of error is by computing a z sub c times sigma over the square root of n. And kind of all those variables are listed in terms of what their meaning is right here. So, flipping to the next page. When looking at the different types of confidence intervals, the only value we don't really know, or the only number we don't have a value for, would be the z sub c. And basically, we'll go through the first two, and then after that it should be pretty easy to find these different values. But when dealing with a z interval, these z sub c values, so for like 80% confidence, the z sub 80 value, it will always be 1.28. Now, how to find that? Basically, what we would do is we would just shade the middle 80% of this bell-shaped curve. Right, so keep in mind, the whole area under the curve is 100%. Just making sure you can see that all right. So the whole area under the curve is 100%. So if we shade the middle 80% of the bell-shaped curve, that would leave you with 80% in the middle, 10% to the right, and 10% to the left. Now, these go back to the problems we worked on before, that if you're given the probability, you want to then find the z-score or the data point underneath. This is a perfect situation to go to your calculator. I can zoom in for you just a bit. You want to hit the second VARS button, go down to inverse norm, and in an effort to find, we'll say, this z-score, I have 10% of my area to the left. So I would do 0.1, 0, and 1. Now the reason I do 0 and 1 is because I'm using the standardized normal curve. So unlike any data points, the standardized normal curve has a mean of 0 and a standard deviation of a 1, right? So a mean of 0 and standard deviations of 1. So if I hit enter here, I get my negative 1.28. It doesn't matter if you use negative or positive, because based on symmetry, you have both the negative and positive case, which is why when constructing a confidence interval, to find the margin of error, we have the plus and minus case, right? So this is the plus 1.28 and the minus 1.28. So that's why we have the plus and minus case. Just in an effort to find the other z-score here, I think I need to zoom back out for you real quick. In an effort to find the other z-score, if you think about it, the area to the left that we could plug into the calculator would be 80% plus 10%, so that would be 90%. So again, I would go back to second VARS. Option number 3 is inverse norm. Now let's do 0.9, 0, and 1, and you should see here that you get the positive 1.28. Right, that's, again, based on the symmetry, you would get those respective values every time. But keep in mind, when dealing with a z-score, the z sub c for an 80% confidence interval would always be 1.28. Okay, so moving on. To find the 90% confidence interval, again, you would now shade roughly the middle 90% of the bell-shaped curve. So if this is our 90%, that leaves 10% for either side, so I would have 5% here and 5% here. So to find the z-scores, again here you would find 1.64 and it would be negative by going to your second bars, inverse norm, 0.05, 0, 1. 5% of the area to the left, and then I'm using the standardized scale of a 0 and a 1. Right, you get your negative 1.64. And of course, to find the positive, you'd have 90% and 5%, so this would be inverse norm, 0.95, 0, and 1, and that will lead you to an answer of 1.64 for the positive z-score. And the same conditions hold. I mean, you do the same process again for the z sub 95 and the z sub 99, but like I keep emphasizing, once you have these values, when dealing with a z interval, they will never change. Right, so those are the 4 values that we need to memorize. Or going through this process, you can derive them. All right. So moving on to the next page. So our first example here. So a study was completed to examine how many hours of sleep college students get per night. So you see here a value for sigma is given. In a sample of 400 students, so this would be the value for n. It was found that on average this group slept 7 hours, so this is your x bar. And then construct a 95% confidence interval. So here, with this information, your z sub 95 from the last page would be 1.96. So everything in the problem must be given to you, and basically you plug it in, you compute the margin of error, which again is this right side of the equation, right? So this is your, I like to say the MOE, or simply just the E. This value is 0.0735, so 7 plus that value gives you the upper bound, 7 minus that value gives you the lower bound. And basically that's your confidence interval, so pretty easy. Now, one interpretation, this is where things get a little bit tricky, is that the interval that you construct will contain the true population mean. Remember, that's with the character mu, 95% of the time. So it's easy to misinterpret this as saying you have a 95% chance of mu being in there, although that sounds pretty good too. The value for mu is either in the interval or it's not in the interval. So if you were to run through 100 different samples, 95 times out of 100, your confidence interval would contain mu, whereas the probability of mu being in this interval is either 0 or 1. The probability is not 95%, right? It says 95% of the time mu is in the interval. So a little bit different, and I can say that again. The probability that mu falls within this interval is either 0, so probability is either 0% or 100%. It's just that 95% of the time the interval would be contained, mu would be contained in this interval, right? So again, the probability of mu being in the interval is either 0 or 100%, right? Because it could either be in the interval or it's not in the interval, but it happens 95% of the time in this case. Okay, so going to the next example. Again, just making sure you can see everything. In a sample of 90 running sessions, so if we just go through and list everything of importance, of running 3 miles, it usually takes Walter 22.5 minutes to run 3 miles. So that would be his sample mean, 22.5. Given sigma is 2.40, construct an 80% confidence interval. So here, your z sub 80 would be 1.28. And basically this is how easy it becomes. You take your sample mean, add and subtract your z sub c, sigma over the square root of n. Everything's given to you, so now it's just a matter of computing the number. So 22.5 plus and minus 1.28 times 2.4 over the square root of 90. So what I would recommend doing in a case like this is do work kind of from right to left. So on your calculator, 2.4 divided by the square root of 90, hit enter, then right away you can hit the multiplication sign, 1.28, and now this value of 0.3238, that becomes your margin of error. So you have 22.5 plus or minus 0.3238 as your margin of error. Okay, so basically the 80% CI, or confidence interval, would be the 22.5 minus 0.3238. Right, so 22.5 minus that number would give you the lower bound. So 22.1762 is going to contain mu, and then to find the upper bound, 22.5 plus 0.3238. That would be the upper bound, 22.8238. So with this, mu is contained in this interval with a probability of either 0 or 1. However, it's contained in this interval 80% of the time. And that's kind of the long way to do it, but even you can see here, it's not very difficult to do so. Now, using the same information above, construct a 90% confidence interval. 99, sorry. So we could go through this. The only number that's going to change, so 22.5 plus or minus, my z sub c, instead of being 1.28, would be now 2.58 times 2.4 divided by the square root of 90. So again, this is the only number that would change because my level of confidence went from 80 to 99%. Okay, so again, you could run through this arithmetic, or to get more precise of an answer, there is a trick on how to do this in your calculator. So I'll show you that trick now. So again, if you hit the second vars button, or I believe, is it second vars? Yeah, so second vars. No, I get those two mixed up all the time. Everything in this class is either found under the stats or the vars button. So for this case, you actually want to go to the stats button. Then the different menu headings up top, you want to go to the calculate. No, the test. Sorry, it's a little early. Okay, so let's go through this again, right? So, stat button, then the menu heading test, then go down to option number 7, which is a z interval. Okay, so then from there, you just want to simply type in everything you have. So your sigma is 2.4, your x bar is 22.5, your n is 90, and your level of confidence is 0.99. So if you hit calculate, you see here you get a range of numbers, and that's essentially your answer. So on the calculator, this process becomes even easier. And just to double check, if we do this arithmetic out, we see that the margin of error here actually became a little bit larger. So 0.6527, we'll say, if we round correctly. Okay, so we've constructed the 99% confidence interval. We've constructed the 80% confidence interval. So what's the difference? And you can see here, in the 80% confidence interval, your margin of error is 0.3. In the 99% confidence interval, your margin of error is 0.65. So your margin of error has increased. So we'll say the margin of error has increased. And we can say the interval became wider, right? So with the 99, your interval is actually wider than in the 80% confidence interval. The reason for that is because you have to be more certain that this interval with a 99% level of confidence contains mu with a greater percentage. That's why this interval must be wider. So again, how do the intervals differ anyway? The margin of error has increased, and the interval became wider since that margin of error is now larger. All right, so moving on. Some facts about the confidence interval. This is more or less what we just did on the last page, right? As your z sub c increases, the margin of error increases. And you can kind of read through this yourself. They are important facts, but in any case, you can kind of just see the distinct differences maybe along here at the bottom when it comes to dealing with the sample sizes and how the sample sizes affect the confidence intervals. Okay, so in this next example, it's one of these think times. In a sample of 90 running sessions, this is what we did in the past. Construct an 80% confidence interval. This 80% confidence interval from the previous page was 22.1762 through 22.8238. And keep in mind here that the margin of error was equal to 0.3238. So we were asked to construct an 80% confidence interval and a 99 using the previous example. So the only things that can change the widths of these intervals, I guess we'll go ahead and list the 99% numbers as well, just so we have all the summaries on all these pages. Okay, so if we compare these, right, we have a 99% confidence interval and we have an 80% confidence interval. And I'm simply just listing these two intervals from the previous example that we did. Right, so we notice that the margin of error went from 0.3 to 0.65. So it increased. And this increase was demonstrated because when looking at the margin of error equation, there's only a few things that can change here. The z sub c. In the 80% example, it was 1.28. In the 99% example, was 2.58. So you can see if you take a number and multiply it by a larger number, it's going to increase this overall margin of error, which we saw in the previous example. Now, x bar is pretty much just given the problem. You have no choice to change that. Whatever that value is, it must stay as that value. Sigma, again, in the problem is given to be 2.40. So whatever the value is, it has to stay as that value. The z sub c, this can change based on level of confidence, and your sample size n can also change on level of confidence. So, not to get too far ahead of ourselves, but when looking at the 99% confidence interval, how much would you need to increase the sample size so that it is the same width as the 80% confidence interval? Right, so in other words, we want to increase this value for n, because as we increase this value for n, it's going to go back and shrink the value of our confidence interval once again. Right, so the z sub c's, as you increase these, the margin of error increases, the intervals get wider. Sample sizes. As you increase this value, the margin of error decreases and your intervals become more narrow. So, if you were to go ahead and look on the next page here, we go through a different example, although what I'm getting here, maybe 2 more pages, is that you can actually solve the margin of error for the sample size. And this is basically all you need to do. So, if we look back to this example, we want to have a margin of error to equal 0.3238. The sample size is our question mark. The sigma is still the same, and our x bar is still the same. So you can see here, everything's the same, except now we're solving for an n and not so much the whole margin of error. And we should also note here that we're using the z sub 99, which is 2.58. So you could have guessed and checked at this, right? So just keep increasing n. Although in 2 pages more in the notes, you have this equation that solves for n, right? So z sub c times sigma all over e, the whole thing is squared. And everything is given to you here, except like I said before, instead of solving for this margin of error, we're now solving for the n. So going through the process of the arithmetic, you can solve that part of the equation for n. Alright, so if we go through this, n is equal to z sub c times sigma, all divided by e, which is your margin of error. Everything that we have is given in the problem. So now the sample size, in this case, would have to be 2.58 times 2.40, all divided by the margin of error of 3238, and the whole quantity will be squared. So again, to recap what we're doing here, in an 80% confidence interval, we had a certain margin of error of 0.32. Then we increased our level of confidence to 99%. when you increase the level of confidence, your margin of error increases because we're multiplying by a larger z sub c value. To bring this margin of error in a 99% confidence interval back down to an 80% confidence interval, we're going to increase the value of n, which would decrease this margin of error. So to find that value for n, we went 2 pages ahead of our notes, and now simply I'm going to type all these numbers into the calculator. So 2.58 times 2.4 divided by 0.3238, square that value, and now my n would be 365.6, so we'll just call that 366. So now what this value gives us, if I were to plug my sample size of 366 in instead of 90, this margin of error would be more like what it was before with the 80% confidence interval. So a lot to take in here, but this is kind of a think time, and it will take you a little bit while to get through this this process. Okay, so to figure out, or to see what happened here, x bar plus or minus z sub c sigma divided by the square root of n. So we have 22.5 plus or minus 2.58 times 2.40, now divided by the square root of 366. So I'm essentially just checking my work here with the 99% confidence interval. So 2.58 times 2.4 divided by the square root of 366. So you see here the margin of error, 22.5 plus or minus 0.3236 or 7 or so. But in any case, this margin of error with a 99% confidence level now references what we had before. So it's kind of a seesaw battle. The z sub c's raise the margin of error, and the sample sizes decrease it back down. So you can kind of go in a circle to keep that value in a certain range. All right. Moving on here. This is the page we just talked about, right? Solving this equation, the margin of error part of the equation for your sample size. So this is a good equation to know. Although you could just keep plugging in values for n and essentially solve for that margin of error. Flip the page over here. I think this is flipping the page back actually, but this shows you how that sample size, if you increase from 36 to 72 to 144, what it does to the margin of error, right? So as you increase the sample size, you'll notice here that your margin of error goes from 0.2 to 0.1 to 0.10. So it decreases the overall sample size. Decreases the overall margin of error. So increasing sample size decreases the margin of error. And then here's another example that you can try by yourself, but essentially n would equal z sub c times sigma all divided by e all squared. The z sub c in this case would be a z sub 95, that's 1.96. And I'm just reading into what's given here. The sigma is 25. To be within 5 days, or 5 minutes, sorry, that would be the value for your e. And whenever you see that word within, right, so that's a key word within, that usually is going to reference your value for e. And then, okay, so here, you're not given a value for x bar since you're simply trying to determine the sample size that would need to construct the interval. So you actually don't need anything else besides this, right? You have your z sub c, you have your sigma, you have your e. So all that we're trying to solve here is our sample size and not actually construct our level of confidence. So plug these numbers in and you have it. Okay, so the z interval description anyway took a little while. The t interval won't take nearly as long because there's only one major difference here. It's basically the exact same process, except now you can see here this is the most important part, and really from the sake of the class it's going to be important to note what you have and what you don't have. So again, this is dealing with a t interval and not a z interval. And the big difference, if sigma is known, you must use a z interval. If sigma is not known, use a t interval. And again, all the process is the same. Remember, sigma stands for the standard deviation of the population, whereas S stands for the standard deviation of a sample, which is a lot more likely to be found. So going through, you can read through this yourself, but in a z-interval, you have those 4 numbers that we found at the beginning of this lecture, and in this t-interval, these t sub c's are what they would be found from your chart, right? So this is table 4, which is your, which I don't think we've used this yet, but table 4 is dealing with the t-scores, and basically this can tell you any t sub c value along with probability that we'll get to a little bit later on. Okay, so if we kind of scroll down here, right, find the critical value for t sub c for a 99% confidence interval with a sample size of 5. Now, whenever you're given a sample size, it's important to note that the degree of freedom, or the DOF, would be your sample size minus 1. So in this case, your DOF would be 4. So we know the degree of freedom is 4, and the confidence level is equal to 99%. Now, how to use this chart? Along the left-hand column here, you see the DF, that's the degrees of freedom. If you go down to the 4, and then scroll over to the confidence of 90, I think it was 90, what, 5% or 99%? 99%. Right, so left column is degrees of freedom, has 4. The top column here is your level of confidence, so we want to go to the 99%. Where those two numbers meet, here we have 4.604. That would be the t sub c value that you would use. So z intervals have the 4 values, and that's it. T sub c's, they could be any number in this chart and beyond, really. So for this first example, if you're dealing with a sample size of 5, the degree of freedom is 1 less than the sample size, then the level of confidence is 99%, which is given. And you see here, it's kind of highlighted in the chart. On the left-hand side of the chart, you go down to 4, over to 99% level of confidence, and the t sub c that we're looking for, oh, it's already listed right here, is 4.604. And then really from there, it's the same process as before, and you're good to go. Let's try another one of those, perhaps. Okay, so find the critical t sub c in each of the cases below. So here, a 90% level of confidence, and the sample size is 9. So here, the DOF would be 1 less than your sample size, which would be a 9. So for letter A, go down to the 9, over to 90% confidence interval. So the answer to this first question would be 1.833. So 1.833, and this is their value for your t sub c. Now, letter B. Again, same level of confidence, and now the sample size is 14. So the degree of freedom would be 13. So then to find the t sub c value, same process. Degree of freedom down to 13, 1 less than our sample size. Then over to the level of confidence, which is 90. And where those two columns and rows meet, you have your t sub c value, which in this case would be 1.771. Okay, moving on. Sample size of 24, so DOF would equal 23. And now the level of confidence is 95%, so the degree of freedom 23 over to 95%. Really, just, the tricky part here is just keeping your rows and columns lined up. Okay, so in this case, you'd end up with 2.069 as your t sub c value. And then we can just continue this down. The degree of freedom here would be 80. The degree of freedom here would be 45. Your t sub c value for letter D would be t sub c 80% level of confidence. This would be 1.292. And with the 99% level of confidence and degrees of freedom being 45, your t sub c value would be 2.690. So one note here, I mean, for all these examples, our degree of freedom landed exactly on a row on our chart. Had that not been the case, so let's say for instance your degree of freedom would be 44, you'd want to go to the smaller sample size in terms of your degrees of freedom, right? So again, there's another example here too. So for example, using a sample size of 34, since the degree of freedom at 33 is not listed, you would simply move up to the smaller degrees of freedom and then use that t sub c value. Constructing the t-interval, this is, again, just like we did before, the same exact process, filling in numbers from the chart or from the problem, and now the only thing that we have to change here is your t sub c value, and basically the same exact procedures hold from before. One note here, going back to your calculator, if we keep it straight this time, if you hit your stat button and go to the menu heading test, notice underneath the z interval you see a t interval. So if you use your calculator, go down to option number 8 in this menu, you simply have to just enter the data that is asked, hit calculate, and you're done. Right, so that would actually eliminate all of this work that you would have to do here. So let's try one of them. So we'll do letter A and B here, and then the rest should be pretty straightforward. So we won't. We'll just go through it all. It's no big deal. So in a study of 10 adults, it was found that the amount of trash generated per day was 4.3 pounds, with a sample standard deviation of 1.2 pounds. And here, sample standard deviation. So this is your value for S, which is your giveaway for a t interval. A lot of times it may not be very clear cut as to what you need to use. So 10 adults. If you have 10 adults, that means your degrees of freedom would be 9, using a 90% confidence interval. Your t sub c, degrees of freedom being a 9 with a 90% confidence interval. I think we just did an example like that. 1.833 would be your t sub c. X bar would be 4.3 standard deviation, and I think that's all we can really get from this. So x bar plus or minus t sub c sigma divided by the square root of n. Go ahead and plug the numbers in. 4.3 plus or minus 1.833. See, I'm even making that mistake. This isn't sigma, right? This is your s. 1.2 divided by the square root of 10. Again, with the t interval, this would be an s and not a sigma. I'm just so stuck in my habits there. That's why I put that in there. So 1.2 divided by the square root of 10 times 1.833. Should actually show you what I'm doing here. So I'm just doing this arithmetic. So I have 4.3 plus or minus my margin of error of 0.6956. And then just go through that same process, right? 4.3 plus 0.6956. So what am I dealing with here? This is a 90% confidence interval. That's our upper bound, 4.9956. And our lower bound will be 4.3 minus 0.6956. So lower interval here, our lower number would be 0.3644. That'll be your answer, and that's the long way to do it. Okay, so for letter B, let's just fall back to our calculator and go through some of this. So again, if you hit your stat button, go over to test, and then down to an option number 8. If you enter all the important information, so sample mean was 4.3, sample standard deviation was 1.2, n in this case was 101, and level of confidence must always be expressed as a decimal, so that's going to be 0.9. Right, so 4.3 for x bar, 1.2 for s of x, 101 for n, and the level of confidence was 0.9. Give that a minute to think. So here, the 90% confidence interval would be 4.1018 through 4.4982. And if you did this by hand, it might be a little bit off, but it's really just a rounding error in your calculator, right? So we might be rounding these t sub c values where your calculator is not. But if you're anywhere in the neighborhood of, we'll say 0.11 or 4.11 or 4.09, it's not going to be that big a deal. As long as you're close and in the ballpark, a little bit of rounding error wouldn't be that big a deal. Okay, so next, construct a 95% confidence interval to estimate the population mean dealing with an actual income of a professor. The 3 salaries were listed here, so 45, 35, and 55,000. Now this is a bit different because we're actually just given data. So from this data, we need to find x bar and we need to find s. So to do this, what I would recommend doing is going to your stat button, editing a list. Let me go ahead and just clear this information out from a previous example. So 45,000, 35,000, 55,000. And again, I'm entering this data into my list, and the way I got here is from my main screen, I would hit I would just hit the stat button, and then the first option there is edit, and I entered my 3 pieces of information. The reason I did this is because it may be easy to find x bar, but the value for s is that kind of long, complicated formula that we learned in the first unit. So now instead of doing that, if I went to back to my stat button, over to calculate, option number 1 is 1 variable statistics. So again, stat, over to calculate, option number 1 is 1 variable statistics. If you hit enter twice, your x bar is just given to you as 45,000, and your s sub x is your sample standard deviation, which would be 10,000. So you can see here that the calculator would help you find those numbers for you, which is going to come up big in example 3. So with those pieces of information, we can hit our stat button again, over to test, and you can see as you get better at this, things will be a little bit easier. So stat, over to test. Notice here a lot of it's just inputted for me since I just did it in my calculator. And the only thing I need to change is my level of confidence. Instead of 0.9, I'm putting 0.95. Okay, so again, if that was too fast, I would hit my stat button, go over to my test menu, go down to option number 8, since we're dealing with a t interval and not a z interval. Input the important information, hit calculate, and that kind of saves you all this headache of going through all this hard work. So a 95% confidence interval would be, in this case, 20,159 through 69,841. So if you think about it here, you have a huge margin of error, just really based on the fact that you're only dealing with a sample size of 3. Okay, last example. Construct an 80% confidence interval when estimating the number of miles per gallon a sports car would get. Okay, so the same process as before. X bar we need to find, and S we need to find. And to find these two values, again, if you go back to your stat button, you want to edit the list. I'm going to clear out that list. Make sure you don't hit delete. That kind of causes some headache. And then go through 24, 24. You're simply just entering the numbers, and make sure you take your time and enter the correct numbers. It's even worth a double check. Okay, so once you have all that information entered, if you want to hit the stat button again, go over to your calculate menu, 1 variable statistics, you hit enter twice, x bar is 24, and s sub x is 3.21. So 24 and 3.21. Now if you wanted to go through the whole chart process and find your t sub c, if you're not a big fan of the calculator, your degree of freedom in this case would be 14 and an 80% level of confidence, so 14 and 80%, your t sub c value would be around 1.345. And then you can kind of go through the whole process we did before, although I'm a big fan of just using the calculator in this case. So over to the stat, then to tests, then down to option number 8. And notice here, like a lot of information your calculator inputs for you, and we're dealing with an 80% confidence interval, which is the only thing we would need to change. 24, 3.21. I'll just leave it. It's better to not round anything if at all possible. And again, if you hit calculate here, the calculator saves you that work. So 80% confidence interval would equal 22.886 through 25.114. So really easy here. And again, the interpretation of this confidence interval, one last time. the population mean, in terms of its probability of being in this interval, is either 0 or 1. But the population mean is contained in this interval 80% of the time with a probability of either 0 or 1. So hopefully that helps out. Some homework problems here for you, and let me know if you have any questions.